Okay, for this, these first three were asked to identify exponential growth or decay, and you can do it by graphing, or you can just remember these basic steps. The thing that determines whether it's growth or decay is the base of the exponent. Sometimes this is called the growth factor, sorry. And this thing is not the growth factor, like the 100 right here is not. That's sort of like the initial value. This would be the equivalent of A in this expression. The b, which is the base of the exponent, which is like the 0.25, that's the thing that we call the growth factor. But if you just know it as the base, that's fine. But because that base is less than 1, we know that this is going to be decay. Because when you multiply by a fraction, you shrink a number. It's as simple as that. Now, as far as the y-intercept, for your y-intercept, you just plug 0 into this equation, okay? So we have 100 times 0.25 to the power of 0. But because anything to the power of 0 is 1, you get 100 times 1. So your y-intercept is simply going to be 100, which, shocker, is going to be, it happens to be the number that's in front, that little a there. So your y-intercept will always be 0 as the x-coordinate, because every y-intercept has that. And then the a value will be the y-coordinate. And in this case, it's 0, comma, 100. Now, for the next one, even though we have a fraction like right here, we don't care about that as far as growth or decay. We're only looking at the base, whether we determine if it's growth or decay. Since this is a fraction, specifically a fraction that's less than 1, if it was an improper fraction, something that was greater than 1 or like 1.5, that would be growth. But this is decay because we're raising the base of something that's less than 1. And the y-intercept, again, I don't have to go through all this. I know right away my y-intercept is going to be 0, comma, whatever that value of a here is. You could plug in the 0 and calculate it yourself, but there's no need to. Now, number 3 is a little different because even though we have a fraction right here, again, this is not the thing we determine whether it's growth or decay. What matters is the base of the exponent. This number is bigger than 1, so since we have a base that's bigger than 1, that's a growth or increase, as opposed to the previous two, which were decay or decrease. And by the way, if for some reason b was equal to 1, you'll really never see that, because if you had 1 to the x power, if nothing would be happening at all, it would neither be growing or decaying. It would just be a constant function, essentially. So that's really not interesting or useful, which is why we don't talk about when the base is exactly 1. But here, since the base is greater than 1, we know that's going to be growth. And we know that the y-intercept, either by graphing it or by plugging in 0 and evaluating this, something to the 0 power is 1, 7/8 times 1. The y-intercept is going to be 0, comma, 7/8. You could write that as a decimal, but since it's already written for us as a fraction, I don't see any reason. So that's the first three. Now, we could use the graphs to answer the questions as to whether it's growth or decay as well. But for these, I just want to roughly sketch a graph of these functions. So, and we're going to use what we learned from the last three. We know that the y-intercept is always determined by whatever point is, whatever value the a is, sort of the coefficient in front of the base. So I know my y-intercept is going to be -4. And you can see that this thing doubles each time. Now, I can do it manually. I know by default that I'm taking, if I put a 0 in here, obviously we get -4 times 2 to the 0 power. If I put a 1 right here, it would be -4 times 2 to the first, so it would be -8. So I know that if you put an x value of 1, it would go, instead of to -4, it would go to -8. And then it would keep doubling more and more and more. And to get it to where I can see that on a scale, I'm going to make my scale a little tighter. So since the y-intercept is 4, I'm just going to count by 4. So there's the y-intercept. And then let's say I'm going to count by 4s on the y-axis. But I'm only going to I'm going to use a 1 for my scale on the x-axis. So on the y-axis, there's a y-intercept. When you plug in a 1, it maps to the value of -8. These are all negative values here. Let me put those negative. And this thing keeps essentially doubling. It's increasing by 100% each time. If you picture that 2 as a 1 plus 1, it's increasing by 100%, or it's just doubling. So 4, 8, 16, double 16, you get 32. But either way, you can see exponential growth, but it's growth in a negative direction. So you're getting increasingly negative. So think of this as a debt that doubles each year. So things get twice as bad each year. If you have trouble picturing what I'm talking about here, you can use technology to help you out. You can just put that exact equation into your y equals, and then you can go to your table. You can graph it too, but if I go to my table, it allows me to easily get values for how my function behaves. Now, I can also see a little easier how it behaves at negative values here. So I can see that at -1, it's going to map to a -2. So at -1, it's going to be half as deep below the x-axis. At -2, it's going to be a little bit closer to the x-axis. And if you look as the graph goes up, every exponential function does this at some point. It's going to level off. Now, this is getting arbitrarily closer to 0. So if you just look at that on a standard window, it matches what I did. Even though I didn't look at the graph to graph this thing is behaving exactly how I graphed it, except with a different scale. If you want it to have a similar scale as to what I have now, I can just adjust my y minimum, let it be -32 right here, and my y max, let me just go up to like maybe 5, and that looks more like what I graphed doing it by hand. Okay, so either tool you use, the table, you can plug in values, but we just want to get an idea of what an exponential graph looks like. As far as the domain and the range, one thing that's worth noting, every exponential function, the domain is always going to be all real numbers. You can put any exponent, any number into an exponent. There's no restriction. You can put negatives, positives, you can put 0. So for your domain for the function, it's going to be all reals, and you can say it like that, or you can say from -infinity to +infinity, that's your domain. Now, for the range, it's a lot easier to figure out the range if you look at the graph. Most exponential functions, the range will be from 0 to infinity, but this one's a little bit different. The range here it's actually all the negative values instead of the positive ones. So the range here it actually goes as far up as 0 because it almost touches the x-axis. So that's actually the max value. And it goes as far negative as you want to go. So it goes really from -infinity to 0. And it never actually touches 0. And you can see that on the table here. As long as you scroll up, like these negative exponents really mean 0.00000, and then like whatever numbers right here. But it never quite touches 0. As far as the y-intercept, that's something we talked about already. The y-intercept for this first one would be 0, comma, -4. It'll always be equal to that value that acts as sort of the coefficient that's in front of the base. So that's number 4. Let's look at number 5. It's going to be the same concept. We're gonna sketch a graph of this, and let's look at what's different between this one and the other one. Well, the value of a is different. That's going to be the y-intercept. So if you look at number 5, and I'll just put this in a fresh screen so we have room. But instead of doing it by hand first, look, let's use a table to get an idea, to kind of ballpark what the function looks like. So let's put 1/4, which you can type 1 divided by 4. That's one way you can do that. And then you could put the 10 in parentheses, and then you raise that to the power of x. And let's just graph in a standard window to see sort of what this graph looks like. All right. One thing that's not clear here It might not look like it hugs the x-axis like the last one did, but it will. Every exponential function will do that. So this thing will crawl along the x-axis. What's not easy to see is the y-intercept. It almost looks like the y-intercept is actually 0, but we know that since the y-intercept is always this a value, the number that's in front of your base, we know that it's 1/4, which 1/4 is close to 10, so that makes sense why we would see that. If you want to get a better view, you can always zoom in on your function. I'm going to zoom in right at the origin, and notice how we see a lot better what that exponential function is. So to get a little sketch of that, and the knowing the y-intercept helps us do that very easily. So here's where the number 1 is. Here's where the number 2 is. 1/4 would be right somewhere around here. And an exponential function hugs the x-axis on the negative values typically, and it just blows up. That's just a basic sketch of it. Your domain, again, is always going to be all real numbers, which you can write in either interval notation, or you could write it out in words, or you can write it in inequality notation, but typically my favorite is either interval or just writing it descriptively. For the range, remember, that's your y values. So it seems to go as high as you want because this thing explodes up, whereas the last one kind of dipped down. This one blows up. So the high point of this is obviously infinity. Well, where is it leveling off at? Well, it's leveling off at 0. So the range is going to be from 0 to infinity, 0 to positive infinity, because this is growth, but it's growth in the positive direction. Whereas the other one, the reason that it went to negative infinity, if you look at number 4, it was because of the negative here. That's what made it go down, because you have a debt, and the debt is getting larger and larger. This one you can think of you have a quarter, and then you multiply that quarter by 10 every year. So it's like then you have 10 quarters, then you have 10 times 10 quarters, but the exponential growth blows up towards infinity. And the y-intercept, we didn't write it, but we stated it. The y-intercept is 0, 1/4, or if you want to write it as a decimal, 0.25. For number 6, if you apply what we learned in the first 3 problems, we know that we're dealing with exponential decay here. So we know that this thing, instead of blowing up either towards infinity or towards negative infinity, it's going to collapse. But first, let's look at the y-intercept. So the y-intercept is always going to be this value right here, this a. So 1, 2, 3, 4, 5, 6, 7, 8. Just roughly sketch that. Let me put that in red. There is your y-intercept. And then all we have left to do is state our domain and range and just kind of roughly sketch the graph. Well, we can put this in our table, but the idea is we have 25% each year. Let me put the scale 1, 2, let me just do it for 3 years. That'll be good enough. So if each, step of the function, you do 1/4, that's what 0.25 is, of this thing. So 1/4 of 8 is going to be after 1 year. I'm going to do 1/4 of 8, which will be 2. Then the next year, I'm going to do 1/4 of that. So 1/4 of 2 is going to be 0.5. Then 1/4 of 0.5 is just going to be a really small number. And then you can see this thing if you sketch a little graph of this function, this thing is going to get smaller and smaller. It's never going to go across the x-axis. It's never going to go negative. You're just going to take smaller and smaller fractions here. And you can confirm that by, again, putting it into your table. The domain, just like every exponential function, is going to be all real numbers, literally everything as small as you want to go to as big as you want to go. The range, let's look at the range. It's harder to spot by just looking at the function, by just looking at the equation. So let's see. Well, it doesn't seem to be going below 0. So the minimum value seems to be 0, but it never quite touches the 0, so I don't put a bracket, I put parentheses. But if you go to the left here, it seems to be it'll blow up if you go backwards in time, sort of. So it'll go as high as you want it to go if you go backwards. So the range is going to be from 0 to infinity. We don't write infinity to 0 because we like to put a small number first, the minimum number, and what you could think of as the maximum number. So that's how to graph and identify the domain and range. Now we're getting to the actual applications of these. So we're going to deposit $600 into a savings account that pays this much 3.9% annual interest. And we want to know how much money we would have in the account if after 3 years, if we don't add or withdraw any money. So we don't see the word continuously in here. So it's implied that, and even though they give an annual interest rate, they didn't say compound monthly, they didn't say compound daily, and they didn't say compound continuously. So there'll always be an annual interest rate, but since they didn't specify how to compound it, by default, we compound it annually. So to get your amount after so many years, you take your principal times 1 plus the rate of change. That rate can be positive or negative. In this case, it's positive because we're paying interest, we're not being charged interest. And so we then we raise that to the power of, I like to put the variable t. You can put the variable x, but the idea is how much time you invested. Now, you should be able to understand what goes where. We want to solve for the amount. The principal investment is $600. 1 plus the rate of change is 0.039. If you take 3.9% and you move the decimal place over twice, that's where the 0.039 comes from. And then we do that for 3 years. And then it's as simple as running this into your calculator. And then we just enter that into your calculator. So if you, I made a little goof here. Let me edit this. I typed the 1 twice. I double dip. So there's two options I was trying to show you. You can enter it in this way. And so it'll be $672 after 3 years. Or you can enter it without that plus sign. In fact, when you see these models, you won't see it written like with the 1 plus the R usually separately. The only time they'll separate that is if they're compounding it monthly or daily or something. But this is going to give you the same result as doing it that way. And what makes sense to round? They didn't say what to round to. Well, it's money. So you could round to the nearest dollar, but we usually have money in terms of like dollars and cents. So even though they didn't say round to the nearest hundredth, you should automatically understand that. But it'll be $672.97. For number 8, instead of exponential growth, this is exponential decay, but the value is still the same. Like that, the equation we use is still the same. So you need to know how to apply this formula. So where the 25,000, we know that that's what the car is initially worth. So it's often called the principal, but I like to think of it also as the initial value. So we know that the 25,000 is going to go here. And we know that it's decay, but they didn't give us a percentage of change. What they did give us is, okay, 5 years. Well, clearly that goes where the t is because that's where time is. But then they give us this other dollar amount. Well, before, the other dollar amount was like, that was the solution to the equation that we found. So the 21,250. So what's weird is they give us that value. Now, what did they not give us? Well, they don't give us the percentage. They don't give us the change. So for us to be able to estimate the value of the car in 5 years, the thing is we need we need the percentage change. And actually, I can't put both of these in the same place. This 21,250 is the value of the car after 1 year. So there would be a 1 that goes right here. So what we need to do is for the 1 year value, we need to solve for what the R value is. So we can simplify this equation, solve for R. So to get R by itself, first I move the 25,000 over, which remember is being multiplied right here. And so then I have R pretty close to by itself. Now this thing in parentheses, this quantity, is being raised to the first power. When you raise something to the first power, you don't change it at all. So I really don't even need these parentheses because 1 plus R to the first power is simply just 1 plus R. Now all we have left to do is get R by itself by subtracting 1 on each side. And then this will give us our percentage change. So our R value is going to be whatever this quotient is, and then you subtract 1. So we're going to enter this in our calculator. I can use the alpha y equals function to keep it stacked like this, or I can just enter it with using the division key. Remember, your calculator does order of operations, So there's no need to try to enter this into two separate lines. It'll do this all at once. So we're losing point like a negative R value. That's weird. So we're negative 0.15. Well, this is the rate is a percentage rate. So what does that mean? That means we're losing 15% of our value each year. Now, another way you could have done this, just in case you're curious, instead of plugging this into the equation this way, specifically because they told you after 1 year, if you do 21,250 and you do like this, the growth factor would be 0.85. So that gives you the growth factor right away, and you could use that. So this isn't the only way to do this. So either you could write in the model the amount is equal to our initial value is 25,000 times 0.85, and we want to find out what it's worth after 5 years. You could do it that way, or you could do what I did. The 25,000 is the initial amount, and do 1 plus the negative 0.15 to the fifth power. But these expressions are equivalent. So to find out what it's worth after 5 years, we just run this in our calculator, and so we get $11,092.63. And since it's an estimate, you could round that to the nearest dollar amount. You could round this to the nearest cent. They said estimate the value, but both are correct. Just one is more precise. But either way, you get about $11,000 for the value of the car after 5 years. So the value really depreciates. You notice it's less than half its original amount, even though it's only losing 15% each year. Next, we're going to talk about transformations. Now, if you remember how transformations worked with quadratic equations, like with vertex form, a times x minus h squared plus k. The k in quadratic equations is just like what this -2 is. So this is the parent function. Let me actually sketch the parent function, even though they don't ask you to do this. 3 to the x power, let's do, if you do 3 to the 0 power, that's just 1. Notice how like in front of the 3 is really a 1. 1 times 3 to the 0. So the parent function would look like this. That's the parent function, which is 3 to the x. So without shifting it down by 2. Now, if you shift it down by 2, 1, 2, now the parent function is going to it's going to have the same shape, but it's going to be shifted down by 2. So what kind of transformation is this? You should know that this -2 is a vertical shift down by 2 is the most important thing to know. For this one, there's a lot more going on here. Well, first of all, this right here, the +4, we know that's a shift of up 4 units. Now, this one right here, the -1, but it's a -1 next to the x. This isn't a shift down. It's a shift sideways or horizontally, but those are kind of counterintuitive. This one is shifted right by 1. And then, well, we got a 1/2 in front of this thing. Remember, that's like a vertical stretch, but because the number is less than 1, that's actually a vertical compression. So this thing is going to be shorter, and I like to stay away from saying skinnier or fatter because it's sort of an optical illusion if you say that, and it's kind of counterintuitive if you do it that way. So what it does is it makes this thing flatter or shorter. So it's not quite a vertical stretch; it's more of a vertical compression. Or you could say it's a vertical stretch by half, but compression is a better way to say that. Now, the original function for this one would be 5 to the x. Without all these extra things, the parent function would be 5 to the x, which would, it would be a little steeper than the 3 to the x because it would climb faster, but it would still have a y-intercept of 0, 1, whereas the parent function, it would be up 4 higher, but then it would also be to the right by 1, and then it would also be a little flatter. So the graph would be like a little bit flatter. It wouldn't climb quite as quick. You could graph these on on a calculator to get a better idea. But what's most important, I'm not going to ask you. I'll ask you to do the graphs of like the previous ones, like you saw in 4, 5, and 6. For these, I want you to be able to state, hey, this is right by 1, this is up by 4, this is a vertical compression, or you could just say it's shorter, this is shifted down by 2. That's what you need to be identify what these numbers here, how do they move the graph. For numbers 11 and 12, we're just doing a couple more sketches of these graphs. Now, the parent function for this one is just 0. You just take the base and you raise it to the exponent. So 0.5 to the x. Now, that would by default, if we did this parent function, that would be a decay function. So it would have a y-intercept of 0, the original function, and it would decay like so. So what's the difference between this function and this thing that's transformed here? Well, let's pick out first what each transformation does. What does this plus 3 do? Well, that's going to move it 3 units left. Well, what does this negative here do? You should know that that is going to reflect it. Some people say that it flips it. So this is going to be, instead of right side up, decay function looks like this. If you put it upside down, the decay function will look like this. But we got to do one more thing. We also got to shift it to the left by 3. So it would be like just, let's just go, 3 units to the left, however you want to sketch that. It would be the same shape, but it would lag behind by 3 units compared to what the green function does. So this blue function right here will be the best representation of the y equals negative 0.5 to the power of x plus 3. Once again, use your tools. If you have, your graphing calculator next to you, right now, practice graphing both the function that we want and the parent function. Now, to be able to distinguish between these, I can just graph them and look at what order it gets graphed in. And let me blow that up a little bit. So I can just, when I hit the graph button, it will definitely graph the first one. That's the function that I want to keep. And then it'll graph the second one. That's the parent function. But say you want to be able to distinguish a little easier which one is which. A little tip is, let's say I'll like this one, right? Let me make this line thick. Go over to the left. I just went over left here. Tap the enter button while you're hovering over this. See how it makes that line thicker? Now when I graph it, that's the function that I want, which is what I want to sketch or what I want to, describe. This is the original parent function. Notice how compared to this function, it is one, it's upside down, it's reflected, and it's also starting way further left than the other one. If I zoom out a bit, it's a little easier to see that it's shifted over to the left. So see that little curve right there? That's the same kind of curve that we have right here, but the thicker line it starts earlier in time. So it has like a 3-second head start. That's what this plus 3 you can think of meaning. But it's shifted over to the left by 3, and it's reflected across the x-axis. For the last one, we have, just as much going on here. You should know, what does this minus 10 do? This is going to shift the graph down by 10. It's not shifted right or left. Notice how this one had x plus 3, but this one doesn't have anything plus or minus added or subtracted to the x. So it's not shifted left or right. But the parent function, if we want to identify the parent function that we're comparing it to, is 3/4 to the power of x. Well, we got one extra number here, so we got a 6. Well, what does the 6 do? The 6, unlike what we looked at for number 10, see how when we put a 1/2 in front and made it shorter, it was called a vertical compression? This is going to be a stretch, so a vertical stretch, or you could see it as like, just make it taller if you want to put it in just layman's terms. And then the negative right here, this is going to reflect across the axis. So compared to if you draw the original function, the parent function, which I'll graph in black, it is exponential decay. So like the 3/4 to the x, because the number 3/4 is less than 1. But for the new function, I'll graph that in red. It's going to be shifted down by 10, so it's going to be way further down. The negative is going, well, let me shift it down last because we've got to do order of operations. So first, multiply it by 6. So this thing is going to be like a lot taller. It's going to be multiplied by 6 because it's going to be taller that way. But then it's going to be upside down. So it's going to be steeper because of the 6. But it's going to be upside down. And then it's going to be shifted down by 10. So it's going to be like way down here. I'm running out of room, but this is what it will look like. Again, I'm not going to ask you to graph these. What I need you to be able to tell me is how they're translated down, left, right, up, stretched, reflected. This one's down 10, stretched by a factor of 6, and it's reflected across the x-axis. All right, that'll be the end of part 1 of the video solution.